Good morning, folks. This is Todd Coburn of Cal Poly Pomona with lecture 13 of Aero 4080. Today we're going to get a really brief introduction to FEMAP. You folks already know how to make your models directly in NASTRAN by creating your input deck, doing that just as a text file. And that actually is probably the fastest way to create most simple models. However, you'll find FEMAP and PATRAN and pre and post processors like that enable you to make more complicated models more readily. Today we're going to take a quick look at how this is done. Okay, so before we get started, you're going to need FEMAP on your computer. Fortunately, you can get FEMAP with NASTRAN for free by registering with the Siemens website. You should have done this at the start of the class when I introduced this information at that time. Now, if you did, you're already ready to get rolling. If not, do that now before we move on, because you might want to try some of this as we go. So once again, we're going to look at the basic building blocks of developing a FEMAP model. We're going to start out by opening FEMAP. Once you've loaded it on your computer, you're going to open that, and you're going to get a window like this. You're going to reach up here. You'll notice you have your set of commands up here. You're going to pick File and then drag down and select Save As, and you're going to input your file name just like you always do. Okay? We're going to use our same naming convention for our FEMAP models. You'll notice when you start off, you're going to be creating a lot of models. You'll be making new models and deviations of the same model, and you will think that you're going to remember all that. But as you get more and more models under your belt, you're quickly going to lose sight at which model does what. So it's important to name these appropriately and to develop a filing system both with folders and NASTRAN runs. If you put each NASTRAN file name in a different folder, then it's easier to keep track of all the files associated with that run. So you're going to put in your file name using whatever folder structure you can use, and we're going to find that a lot of what we're going to do is using the Model tab. There are actually a number of options with FEMAP. It's intended to do a wide variety of things. As you become more experienced in FEMAP, you'll learn many capabilities beyond this, but actually to do the most basic models, you aren't going to need to use, you're only going to use a piece of the capability of FEMAP. So we're going to be looking for this Model tab up here, and you're going to notice that FEMAP is impatient. As soon as you start creating elements, it's going to need to know what those elements attach to, what materials are used, what are the properties, and things like this. So we're going to kind of do things in reverse, where normally when we're making a NASTRAN deck, we're going to start by putting in our nodes, our grid points, and then our elements, and then we'll start putting in the properties and the materials associated with those. We're going to do that backwards, and we're going to create all of our materials first, or at least some of them. So think about what kind of materials you're going to need, and we're going to create those. Then we're going to think about what kind of elements and what properties we have with those elements. You're going to create your property cards. Now you can create your property cards immediately before creating the element, but as soon as you create the element, it's going to want to know what property is used. You can also go and use a dummy property, then change into the other properties, but that's got the risk of missing some elements. So if you create your properties up front, then you can assign them as you go. Materials first, and then properties, because when you create the property, it needs to know the material, so you need to have already created the material. When you create the element, it's going to want to know the property, so you need to have already created the property. When you create your element, you're also going to have the nodes, so we're going to have to create the nodes before we create our elements, and so forth. Okay? Then we're going to go to running our model, and we're going to have to put some structure together. Where NASTRAN was pretty simple, when you work right in the NASTRAN deck, you can use the same basic case control deck and executive deck for most models with only minor tweaks. Now we're going to have to go through this picking process. We're going to have to pick a lot of things in order to get, and a lot of that's going to ask for capability that we just plain old don't need. So we're going to have to go through that systematically and keep alert to the different kinds of things we can do. Okay? So with that said, let's see, we said this, and we said this. Okay, here we go. Are you ready? All right, so first we're going to create some material data. So we're going to do that by selecting Model. We're going to drag down the pick menu to Material. There's model right there. We're going to pull that menu down and select material. When we do that, it's going to open a material window that looks something like this. Okay? You'll see that this is supposed to be a what you see is what you get, and actually it's fairly simple. Not as easy as just putting in the information on a single card, a single line in NASTRAN deck. But you're going to put in your modulus of elasticity, you're going to put in your shear modulus, you can put in Poisson's ratio, you can put in 2 and let it calculate the third, or just put in all 3. You can put in your coefficient of thermal expansion. You're not going to need that for most of the models until we get to thermal runs. But you won't need the conductivity for anything we're going to be doing. Specific heat is something that you can do with other models, nothing that we're going to use. Heat generation factor, you can just leave these all 0. If you wanted to go and later calculate stresses or margins of safety, now we're not going to do that yet, but if you wanted to do that, then you could go and put your allowables in for that material as well, like your FTU and your FCU and your FSU, okay? Your material density, you mostly aren't going to need unless we go into dynamic loading, but you can put that in, and sometimes NASTRAN will struggle if you don't have it, even though it doesn't need it. So you can go ahead and put in a little density value here. You aren't going to need damping or a reference temperature for the stuff until we get to thermal analysis, and you can throw in a reference temperature, okay? Is that all this? All right. So then we get to our property window. To put in our properties, we're going to select model again, and then we're going to drag down to property. See that? Once we get property window open, we're going to get something like this. This is actually a plate element property. Once you get the property window open, it's going to ask you what kind of property. Do you want a rod property? Do you want a bar property? Do you want a plate property, right? So this is a plate property, which is going to encompass the C quad 4s and those kind of elements. You're going to put in your thickness. You can put in a title for it. It's a good practice to put in what a title for your properties. Let's see. So most of this you can leave blank. You're going to put in a thickness. Mostly you just need to put in the first thickness, T1. If you only put in T1, it's going to assume all the thicknesses at all 4 corners are the same. That's actually the best approach for most of what we're going to do. But this does allow you to put in the thickness at each grid point. 1, 2, 3, 4 is not associated with grids 1, 2, 3, 4. It's once again related to the pick order. The first node that you pick when you identify the node from like 33, 34, 39, 37 would be 1, 2, 3, 4 would be the same sequential order, okay? So then you're going to put in, if you wanted to put in a parameter of different bending stiffness than 1/12 pH cubed, then you would do this in this bending stiffness parameter. Or if you wanted a shear parameter, you could put it there. Mostly we're going to leave those 0. If you wanted to put in, now remember, if you leave the bending, transverse bending, and bending membrane coupling blank or 0, then what that does is you will only have a membrane with only axial and shear capability. That's what we're going to do mostly. If you ever are modeling a plate where you actually wanted to have transverse bending so you could load the plate transverse to the plate, then you'll need to put a material ID in the bending box, third from the lower right. If you want a transverse shear stiffness, then you're going to need to put one there. We're going to always leave the transverse shear stiffness and the membrane bending coupling as 0, as you should always do in all models you ever use until you become an expert user. Most people that think they're expert users and are regarded as expert users actually aren't. They're maybe good at pushing buttons, but they don't really understand all the details of what they're doing. You should not be putting material properties in these boxes unless you have thoroughly tested and know exactly what it's doing. So for most of the time, our membrane elements like this will just be having membrane stiffness. We will also often use plate where we want through thickness. So if you're modeling a skin, that should just be a membrane in plane or a C shear panel. But if we're going to model say a plate, we're going to have loading, transverse loading on the plate because we're idealizing like the top of or a bulkhead and a rocket with pressure or something. That's where we're going to need that bending stiffness. And that's where we'll put in a material property under the bending one. Okay? And then if you click these boxes, top fiber, bottom fiber, that will allow you to recover stresses from your element. Mostly, the most practical models for most aerospace use are models that are designed to develop good loads, not to get stresses. A lot of folks are trying to get stresses out of the model. Mostly those folks don't really know what they're doing. they don't realize you don't just write a margin of safety on the principal stress. That can be done for the skin and structures like that, but for most of our lightweight structures that we have, we're going to be needing to evaluate other failure modes like crippling, buckling, and other things. So mostly we're looking for a good model for loads. Okay, we said all this, and I believe we said all this. So actually this comment about putting a bunch of .002s, I recommend leaving, obviously these other thicknesses blank. You're going to put in nothing in the transfer shear or membrane bending coupling. You're going to mostly leave that bending stiffness 12I over T cubed also 0. Okay, you're just putting in a title, putting a thickness for the whole panel in T1, and occasionally you will also put a material property ID in the bending stiffness 1. You got that? Okay. All right. With that said, we're ready to move on, and now we can go and this is just reminding us that we can go edit those. Let's say you aren't sure what you put in, or you need to add one, or need to change one. You can go in there to modify, edit, and then you'll choose property or material and do what you need to do to change those. Okay? All right. Now, the next step, now that we have properties and materials shown, we can put in our grid points. We actually could have done that before we made the materials and properties. And there's a bunch of different ways in FEMAP that you can do this. One of them is just typing in the coordinates. Others use offsets from various coordinates. You can just put in each one systematically one by one. You'll find for many of the models we generated with NASTRAN, it's quicker to just put it in your NASTRAN window. For more complicated models, this has a lot of capability to do rapid modeling of IDs. Now, FEMAP often offers potential to go in auto mesh, just create geometry that then you auto mesh into grid points and elements. That's pretty powerful for certain kinds of things. It's mostly overused. It's actually for coarser models with fewer elements. It's better to keep track of what's numbered how. But there is a lot of practical application for doing the auto mesh also. But I'm going to encourage you for smaller models to systematically do it step by step. Okay, we could have also created a coordinate system in here as well. Mostly if you don't, you're just going to be using the global coordinate system as we go. All right. Once we have our grid points, we then are ready to put in our elements. So you're going to create those, you're going to go back to model, you're going to choose element, and then you're going to choose your element type. And then you're going to choose what nodes it connects to. So if we're putting in a bar element, we're going to choose 3 nodes, right? Or 2 nodes in a vector. And you'll notice this has the ability to put in pins and offsets and other things. We're mostly going to not do any of that unless we absolutely have to. Okay? And this is telling you step by step how that is done. All right. Now, a lot of times you're going to start creating elements and things, and you won't see where it's appearing on the screen. It's hard to tell in FEMAP. But what you can use is adjust your view by, or do this periodically, pick view and auto scale all, and that will kind of fit your model in the window. And then you can also rotate and choose different views, or even create views as you wish. All right. We have a model. It's not fixed to anything. It's got no constraints. It has no load. So let's go ahead and add some loads. To do that, we're going to select model, load, and one way to do that is a nodal load, where you're applying loads, forces, moments at the nodes. And then you can go and put in, you can name what they are, give it a title, and give it a where it's applied, at what grid, at what nodes. You can tell we can put in multiple nodes from node 2 to node 3 or 5 or 9 or whatever. You can pick a vector or a direction and put in a magnitude. Okay. Here is a force vector, one of the pick menus for a force. You see you got force, you got moment, you can put it in force displacement and force rotation and other things, okay? So we can put it in as components. You notice you can put it in as vector. If you put in components, you just put in the value or the magnitude in the fx, fy, or fz. If it's off at some wacky direction, you might need to enter a vector or something, okay? So then we're going to go and this is showing the nodes that we just applied. Then we can exit out of the load generation subroutine. We then are going to add constraints. So in this model, looks like we've got a cantilever beam going here with two forces applied. You're going to pick model constraint, and a nodal constraint is one of the common ones we'll use. You can put in a title, you can put in what grid point it's applied at, and then put what degrees of freedom, 1 through 6, just like we did before. Okay? And then cancel out of that when you want to exit that. Okay. Once you've got that, we then can prepare to make our NASTRAN run. Okay? So first we're going to have to tell it what kind of run we want, what kind of data we want back, what loads and constraints that we are going to use. So we have created some loads and constraints, but just because we created them doesn't mean they're going to be in this particular run. So remember, in the case control deck, we had to specify what constraint, what SPCs, ID 1, for all the 1 to apply that to our model, and what forces we're going to be using. In the same way, we're going to have to do that in these pick menus for FEMAP. So you're going to pick Model, Analysis, New, and then it's going to open a pick window like this. Okay? Once it does that, you're going to, you can put in your title. It's going to be a NASTRAN Run. This allows you to use other programs if you had other programs installed on your computer. And we're going to do a static run, right? Most of the runs we're going to do in this class will be static runs. We'll do a little bit of buckling runs a little bit later, and maybe even a nonlinear run. Actually, I'm not sure if the student version has the nonlinear. I'll have to refresh my memory on that. So it's going to ask you a number of details that you're going to not understand, and just kind of wing it when you go through those, or leave it blank unless it doesn't work. Okay? So we can see we've got NASTRAN chosen, we've got a static analysis, and we then can go and tell it what cases we're going to use and that kind of thing. All right? We're going to click the plus next to the master requests and conditions, and then we can go and click through each of the options. You can see we've got boundary conditions, we've got our constraints and our loads there under boundary conditions. We've got our output requests. Looks like we've got displacements and applied loads, and the constraint forces and the forces, stresses, corner results, which will give some nodal data, and that kind of thing. Okay? Now, you can say, like, this has post-process only as the destination. A lot of times we're going to want to also see our FO6 file. Okay? Once we're done, we can choose Done, and then it's going to run. You'll see over here to the left, on the window to the left, it's got some information that will spit out at you as it runs, and then it's complete. Now, when it's complete, it's going to be rather uneventful if it runs properly. And what you're going to have to do, it looks like here we forgot to pick File and Analyze. Once we do that, we have our run. Once our run is a success, we're going to have to pull our data back. We're going to have to pull the data back into our model. Okay? The way we're going to do that is we're going to pick Load Results, and that will load the results. You'll pick which result file you want. Once you have that, you can look at the stresses or the loads or anything else. Okay? Once you have those input, you can then go and show like a deflected view of your model like this, right? Like view deformed or undeformed structure. Okay? If we select view and then select, we can select what view we want to see. You can see here we've got the model style, hidden line, deformed none, contour none. Pick OK. We can pick a beam diagram and then deformed and contour data. And if we do that, we can pick what load case we're going to show. And like, for example, if we chose bar end A moments in the deformation contour slots. You pick OK again, and it will show this. So normally what NASTRAN is going to do is give you a color plot like this showing various loads or stresses, and it will just be the color of the line, which is hard to read. But the contour plot that we just did, the last slide that showed how we would get a contour on there, is actually showing the contour on it. And this is just like a bending moment diagram or a shear diagram if we had chosen shear. You can see here that this is showing down in the lower left corner. It says we've got NASTRAN's case number 1, whatever you defined as case 1, whatever that loading was in that set of constraints. And it can see we've got the contour shown for bar end A, plane 1, moments, the moments in that plane. and you can see that our moment is going from whatever that is that minus 900,000, that purple, up to, at the other end, basically 0. So we can see, and this makes sense because we were fixed at the left end, we had a loading at the end and in the middle, so we see our moment is building up. So this is really cool. Now this is just a beam elements, but we can do the same thing later when we're making frame models with a floor beam, showing the bending moment diagrams on those elements and showing the shear diagrams on those elements. We'll make it really quick to see what spots in our model are maximum so we can do hand analysis to determine if our model is good. This is very good for showing visual loads, is very impressive. If we had created our model using quad elements or C shear elements, we wouldn't be able to do that. We'd be able to see the stress distribution in the element itself, but we wouldn't be able to see a shear and moment diagram like we're seeing the moment diagram here. So this is the beams and the bar elements allow you to do these shear and moment diagrams, which is another reason why bars, C-bars, are a really good element to use for like frames and floor beams and things like that. It's very easy to understand, very easy to understand where our max loads are with these kind of plots. Okay. This is our bending moment diagram. We can plot our shear the same way. We can plot our axial load, whatever else. Now for each of these, you're not going to plot them at the same time. You're going to have to plot one at a time, and then you would show those separately in your model. You'd show, here is my model. These are the bending. This is the bending moment diagram. Now the trick is, remember, when we're doing our NASTRAN elements, we have our little plane. Remember, we have our two planes. We have our plane 1 bending, which is like this, and our plane 2 bending, which is like this. Now if we define our properties, let's say going around a fuselage, all consistently, then the bending moment diagram will be consistently. But if we were careless and we made plane 1 this way for some elements and the other way for the other elements, then our beam, our shear and moment diagrams will be nonsense because they'll be flipping back and forth between different coordinate systems, basically. Okay. So this is a very powerful tool that is available in FEMAP. Okay, we can then choose tools text, and then it allows us to go and name, put like an identifier in here. So like a good thing would be to go and put in whatever your information is, like if for this Aero 4080 project, whatever, Alice Cooper doesn't want to lose credit for his work, so put it right here, showing your name in your model. This is just a text in the window that shows that this is your model. It's a really powerful way of taking credit for your work. You can also put things like, hey, put a descriptor. Since it's kind of hard to read this color plot, you can annotate this with what the actual maximum moment is and what the actual moment is in various places or things like that, or put in what factor of safety is included in your loads or other information. Okay? And so on. Okay, so that is a really brief introduction to FEMAP. Those of you that want to use Patran, if you loaded the MSc NASTRAN Patran, you are welcome to use Patran. I have not developed a tutorial for Patran, but there are a number of those out there that you can go and pull up. The beauty of learning Patran is most of the bigger companies like the Boeings and the Northrops, the real aerospace companies are going to be using NASTRAN Patran mostly. Some of them will also use Abacus, often out of Patran as well, because Abacus is a really good nonlinear solver, which is actually overused, but it's very powerful for the things that it is needed for. Those of you that are learning FEMAP, that's fine. FEMAP is used by more of the smaller companies because it's quite a bit less expensive. They're both very expensive. But okay, so those are some ideas. You can create your next project that way, and I don't recall if it's actually still Project 7. It may not be. I need to take a look at that and change that. Okay. Once you've created your model, I encourage you to play with FEMAP. Maybe go back and create some of the other projects in FEMAP now that you've done it in NASTRAN. You can do it really fast by making your NASTRAN deck and then just read in your NASTRAN deck into FEMAP. You can go to, you'll notice you can import a NASTRAN input deck, a BDF file, and it will generate all your data in FEMAP from your BDF. So if you really like making your NASTRAN models that way, you can read them in. However, it's good practice to go and create those from scratch with FEMAP. Now that you know how to do it directly in NASTRAN, learning how to do it directly in FEMAP is very powerful as well. Okay? These are a few additional videos. There are a number of FEMAP tutorials out there. You're welcome to go find your own. Autodesk has their own. MSC NASTRAN has their own. Actually, MSC probably has Patran videos. Siemens has their own, and these are a few. These aren't necessarily great. They're just a few that I grabbed and threw at you. So you're welcome to go take a look and play with those as well. Many of the tutorials out there are going to teach you to make things that look really complicated really fast. And as you probably have sensed, I'm going to recommend keeping it simple. That doesn't mean it's not valuable to go and make some of those models. If you've got a tutorial, go ahead and follow what they're doing and see what it is. But I want you to become suspicious of anything that creates a lot of input. The higher elements, the more complicated elements, mostly bring back a lot of input that it's very difficult to decipher what it actually means or if there's an error. So this is just to get you started. That is a quick tutorial for FEMAP. Go in there, practice, and enjoy.